Okay, so here we want to explain how do we answer typical exam questions on direct current theory. So I have gathered a few questions here that I want to use to explain how do you go about it, how do you answer typical exam questions on DC circuits. First thing first, be able to see that this circuit, how is the arrangement? How has it been arranged? As a matter of fact, we ought to know or we ought to understand that our circuits can be arranged in series, in parallel, and in series parallel. So oftentimes we need a series or series parallel circuits in the exam because they are combining now everything. So how do we know in the first place that these resistors are in series, these ones are in parallel, and these ones are in series parallel? So it's very easy to note. What do you do? Here is my advice that I always give. I always say that in order for you to know how are the circuits arranged, or how are the resistors per se, how are they arranged, what you need to do is you have to follow the direction of the conventional flow of current. So in our case, like you see these arrows here, they are pointing to the direction of the conventional flow of current. For as long as current is divided, for example, I'm going to give here at this point, you can see that current has been divided, some current going towards this direction and some current going towards that direction. That marks the beginning of parallel combination or the parallel circuit. In other words, I'm saying for us to easily denote or see resistors in series or in parallel, what we simply do is we check, has current been divided or not? If for as long as current has been divided, definitely it means that those resistors experiencing the divided current are indeed parallel. But for as long as resistors are experiencing the same current, then we can safely also say that they're in series. A very good example that I can give on the circuit that I have there is that it's of course we have agreed that this current here has been divided, which means all resistors in this direction of current and all resistors in this other direction of the current, they are in parallel. Those two groups, they are in parallel, right? But let's follow this current that is going down, I2. Let's follow I2, right? If we can see current I2 is going to be the same current that will flow through these two resistors as well as these two resistors here, which means this whole group of resistors in their combinations that they have, they are also in series. Why? Because they're experiencing the same current I2. So we can also safely say, for as long as resistors are experiencing the same current, or for as long as the same current is going to flow through the given resistors, then those resistors are in series. That's what we are trying to say right now. And for as long as resistors are going to experience divided current, or as long as current is going to be divided among resistors, then those resistors are in parallel, right? So how many parallel combinations do we have? Let's try to figure them out together before we answer the questions. It's very important, right? This whole branch here, this whole circuit, this side, I1, we have agreed that since the division of current IT, the total current has been divided at this junction or at this node here to have I1 and I2. It definitely means that these resistors on top are parallel to these resistors that are below, right? So that's first combination we are seeing. Let's call it RP1. Right, so we see these resistors are in parallel. Which ones? The 50 ohm is in parallel with all these resistors. The 60 ohm, which means this one, the 80 ohm, this one, the 40 ohm, this one, the 30 ohm, this one. All these four resistors are in parallel with the 50 ohm. How did we see that? Because of the division of current here. Right, so that's the first combination we are seeing. Right. Which other resistors are in parallel that we are seeing? Okay, if we follow IT here, we see that it's going to be divided in this junction that I'm marking. Some current of I2 going towards this direction, and some current of I2 going also towards this direction. It means that the 60 and the 80 ohm, they are also in parallel. They also form another parallel combination, right? Apart from them, we also see the 40 ohm and the 30 ohm, R5 and R6. They are also in parallel. Together, they also form another parallel combination. So these are the parallel resistors that we are actually having in this regard, right? So let's try to answer the questions then together, okay? So the first question they were saying, calculate the total resistance in the circuit, right? So that's our first question there. So how do we go about it? How do we answer that question? Right, so let's try to answer that question together, right? First things first, let's identify, as we have said, we have identified the resistors that are in parallel. Now, having identified them, what is the next thing? Of course, knowing very well that how do we calculate resistors in parallel and resistors in series, how do we calculate them? Right, for resistors in series, we are saying total resistance RT is equal to, of course, the sum of the resistors that we are having. Then, for parallel combination, how do we calculate the total resistance? It is the ratio or the sum of the ratios of the resistors, right? So let's try to do that, okay? So we start first with the parallel combinations, right? So I will start with this. Why? Here is my advice. Whenever you are performing calculations, try to start from the furthest point away from the source. Why? So that you try and minimize your circuit as you are going. So we say this combination here, they're in parallel, the 40 and the 30, they're in parallel. So I will just call them my R or RP1. It doesn't matter actually, it's RP2, RP3. We are saying it is a parallel combination. But we are saying, let it be the first parallel combination we have. It doesn't matter actually. Okay, so how do we calculate? For two resistors, we can use the formula product over what? Over sum. So if we are not familiar with this formula, we can actually use product over sum. So we are simply saying 40 times 30 over 40 plus 30. Or we can actually use the formula 1 over RP is equals to 1 over R1 plus 1 over R2. So in our case, it will be 1 over R5 plus 1 over R6. And then we invert the answer after that. We are still correct. We will still arrive at the answer. Okay, so I will opt for this one here. So directly 40 multiplied by 30 divided by 40 plus 30. If we punch that correctly on the calculator, we are going to get 17.143 ohms. That marks the resistance of this first branch here, right? We call it the equivalent resistance or the effective resistance of that particular branch. Let's go to the next branch. Let's calculate its effective resistance as well. So we will call it RP2. As a matter of fact, I was saying it doesn't actually matter. Is it RP what? Whatever. We're just saying it's a parallel combination. Okay. So let's calculate. RP2 is going to be also product over what? Over sum. 6 multiplied by 80 over 6 plus 8. Right. So if we punch that on the calculator, we are going to get 34.286 to 3 decimal places, right? That's RP1 and that's RP2 there, right? So what is happening? RP1 and RP2 are now in series. So the main reason why we need to start from the furthest point away from the source is we'll be trying to minimize our circuit as we are going. In other words, we are saying our circuit now looks like this. I hope we are still following each other. I just want to quickly show you how our circuit now looks like. This is the 60 ohm resistor that we see. This is the division of current here. And then that's the 50 ohm resistor there on top. Okay, that's the 50 ohm resistor there. And of course, that's the path which is going back to the source. Then we have these two resistors, these two pairs of resistors. Resistor RP2, the one we labeled RP2, and the one we called RP1. This is how our circuit now looks like. So the one we calculated is RP2, the one we got 34.286 is this one, the one we got we labeled RP1, the one we got 17.143 is now this one. That's why we are saying start from the furthest point away from the source. You are trying to minimize your second as you are going. This is what I mean when I'm saying you are minimizing what? Your second as you are going. Right? So it means now we are certain these two are in series. So what are we going to do with them? We shall add them. So let's go to them. So we simply add 17.143 plus 34.286. So if we add these two, we end up having 51.429, right? Again, we have minimized our circuit now. How does our circuit look like now? So I will just use this same circuit that I've drawn. So our circuit now, where is this 51.429? Where is it? It's now here. This is now the 51.429. That's what has happened. We are minimizing our circuit. That's why I'm saying start from the 50 point away from the source. Okay, so what's happening now? The 50 ohm, which is this one, and the 51.429 ohm resistor, effective resistance, we now have this one. How are they connected? They are in parallel. How do we know they're in parallel? We followed the conventional flow of current. Then we saw that current was divided at some point, which means those resistors that experience the divided current or that are sharing the divided current are therefore in parallel. So we can also say, let's mark that also as our P3, our third parallel combination. So apparently, what are we going to do now? Product again over sum. 50 multiplied by 51.429 divided by 50 plus 51.429. There we go. So we just simplify that. What do we end up having? 25.352 ohms, right? It means now we have the effective resistance of these two combinations that are now in what? That way in parallel. So we have their effective resistance. Now, this 25.352, what is it? How is it connected to the 60 ohm resistor, which is this one, just after the source, immediately from the source? How are they connected? They are now in series. So it means this 25.352 is now in series with the 60 ohm. So what do we do now to get the effective resistance, the total resistance? We simply say now, let's add the two resistors. So we simply say, therefore, RT, apparently it's the last total, the final combination of all the resistors we have, which is marking the total resistance. So it's going to give us RT is therefore equal to 60 plus 25.352 ohms. There we go. That marks our total resistance. We've answered the first question. So the key or the idea was to start from the furthest point away from the source. That's where the trick lies. Okay, let's go to the next question. The next question is now saying calculate the total current of the circuit. Now, how does the examiner expect us to calculate the total current of the circuit? Now, here we summon Ohm's law. So we simply say current. What is the relationship that current has with resistance and voltage? Because we have them now. Total current IT is equals to VT over RT. And apparently, we have been given VT and RT. We've just calculated it. So we simply take the 50 ohm or 50 volts that we've been given, 50 divided by what is our RT? We have just calculated it. We got 85.35 watt, 352. So 352 ohms. After adding, we added 60 plus 25.352. That's what we got, 85.352. So if we now divide 50 divided by 85.352, we are going to get a 0.586 to 3 decimal places again, amperes. That marks our current. We are answering the question 2.2. Let's go to 2.3. Calculate the current I1, which is this current through this branch. So that's the one that the examiner is now asking us to calculate. There are a number of ways to calculate that, right? I will quickly explain. Number one, there is what we call the current divider rule. Current divider rule simply states that I1 is equal to R2 over R1 plus R2 multiplied by I total. That's what the current divider rule states. But what is the meaning of this? This simply means that if we want the current I1, which we have labeled I1, which has been labeled I1 there, is going to be equal to the effective resistance of this whole other branch, where we don't want to calculate the current, divided by the sum of the two resistances, multiplied by the total current from the supply. Now we have the total current from the supply, we have it. So we can take that advantage, and we simply say R2. What then is our R2? Remember, we had minimized this whole other side of the branch to become 51.429. So apparently that's the resistance that is in parallel with the 50 ohm resistance. So that marks our R2. So we'll say 51.429 divided by 51.429 plus 50, right? Multiplied by the total current of the circuit, 0.586. And that definitely is going to give us a value, which is, if we punch correctly on the calculator, we get 0.297 amperes. That marks our current, right? Having determined this current, what is the next thing? The next thing is I2, right? I used this formula, but is it the only one? No, it's not actually the only one. We could have also used the total current and, of course, the effective resistance of the last parallel branch that we created. Remember, we had that 25.352. What was it signifying? It was signifying the effective resistance of all the parallel branches we have in there. That means it is the one which is now in series with the 60 ohm. If we take the total current, 0.586, and we multiply to this 25.352, we will get a voltage. Apparently, that voltage shall be the voltage of the parallel branch. As a matter of fact, it shall be the voltage of the 50 ohm resistor. It shall also be the voltage of the 51.425. Please check this, hear this clearly. It's another way again of calculating. So after finding this VP, we simply say now I is equals to VP over R2, the resistance in the where I1 is. We will still find I1. If we do the same again for I2, to say VP, where will we have gotten this VP from? From calculating 25.352. Why 25.352 specifically? Because it is the effective resistance of the parallel branches, of the parallel branch. Okay, so it's another way again. So I will not do that. I've already used this other method here. Okay, let's quickly go to the next question. The next question is now saying, so you may try also to do that other method there, and you see that you still arrive at the same answer here, right? I2. I2 now, you can still repeat yourself. You can still say R1 over R1 plus R2 multiplied by I total. I hope it's now making sense that we are taking the resistance where we don't want to calculate, which means for I2, we are taking the resistance the other side. For I2, we will take the resistance of this other branch, which is the 50 ohm. And we say divided by 50 plus. What are we taking here? 51.429. Why 51.429? Because it is the effective resistance of this other side, right? So we can still do that. Or alternatively, we will now summon Kirchhoff's current law. What does Kirchhoff's current law say? It says that the current entering a junction is equal to the currents leaving the junction. The algebraic sum of currents at a junction is equal to 0, or the algebraic sum of currents entering a junction is equal to the current algebraic sum of currents leaving the junction. So we can still say, we can still use that, right? So By so doing, we'll simply say, okay, I2 is equal to IT minus I1, because IT is the current that is entering the junction. I1 is the current leaving, which is 0.297 that we already have. So we'll directly say 0.586 minus 0.297. And of course, we are going to get 0.289 amperes. We have arrived. That marks our I2. Let's quickly go to the next question. The next question is now saying the value of I3 from the diagram below. So here now they are asking about that Kirchhoff's current law. What is it saying? It says the current entering a junction is equal to currents leaving a junction. How many currents are entering? We have I1 plus I3. They are entering the junction. They are equal to how many currents are leaving? We have I2 is leaving the junction. Therefore, due to that, we can create an equation to solve it. 5 plus I3 is equal to 8. We are simply substituting I2, we have it. I1, we have it. We don't have I3. So that's what this question is asking. So making I3 the subject, I3 is equal to 8 minus 5, and that will definitely give us 3 amperes. We have answered this question just like that. Right, so having done that, let's quickly go to the next question. The second question we have here is saying, I refer to the second diagram below and answer the questions that follow. Of course, it's saying calculate the total resistance in the circuit. Again, I want to say, how do you approach a circuit like this? First things first, there are currents that are in parallel. There are resistors that are in parallel and the resistors that are in series. Of course, so it's a series parallel combination. But how do we ascertain, how do we know that these resistors here are in parallel, these are in series? As a matter of fact, if we follow the conventional flow of current again, there is our I total, I'm marking it there. When it reaches this junction, it will be subdivided, some current going towards this direction, some current going towards this direction. Then this current that is going towards this direction, when it reaches again this other node here, it will subdivide. Some of its current going towards this direction, some of its current going towards this direction. So as a matter of fact, I am saying this whole branch that you see here is everything you see this side is actually parallel to everything that we see this side. Why am I saying everything and yet I'm seeing one resistor? So that it clicks in our mind that no matter the number of resistors, it doesn't matter. Whether it's one, there are two, there are three, there are four, they are all in parallel with all the other resistors, the other side, right? So we are simply saying it's key, it's important to note or to know that whenever resistors have experienced divided current or share divided current, they share current between them, then they are indeed parallel. So start from the furthest point away from the source. This is the furthest point away from the source. And we are saying, how are these resistors connected? As a matter of fact, they are in parallel because at this point, current was divided. Now, oftentimes, some students do have a challenge, or should we say, some have a challenge of identifying how are the resistors in really in parallel. Check the junction, check junctions. As a matter of fact, this is not a junction here. This one, what is it? It's just a bend of the conductor. It's just a conductor turning or bending. So that's not a junction. This here is a junction. This here is a junction. This here is a junction. This is a junction. These are the junctions we're talking about. Okay, so as we were following the conventional flow of current reached this point, it was subdivided at this point, which means these two resistors are in parallel. So we start with them first. So let's calculate them. I'm going to call that RP1. So we say 6 multiplied by 4 over 6 plus 4, product over what? Over sum. So product over sum, what do we get? We get 2,4 ohms, which means the resistance of these two resistors, it becomes 2.4 ohms. We call it the effective resistance or the equivalent resistance of that branch. What have we done to our circuit? We are minimizing our circuit, which means at this stage, our circuit looks like this. I'll just quickly display it here. Then I will erase it quickly just to create some space. So we are saying this is our circuit. Okay, pardon my circuit, is a little bit poor. Okay, let me just try to fix that so that it doesn't look a little bit weird. Okay, so there is our circuit. This is how it looks like now. This is how the circuit looks like. Okay, this is the 7 ohm resistor. This is the 24 ohm resistor, R2, and this is resistor R3. I will not label them again. I'm just trying to show you how the circuit now looks like. This is RP1, the resistor we have called RP1. Apparently, this is R4. This is resistor R4. This is how our circuit looks like. So RP1 is now here. How is it connected with these other resistors? So RP1 is actually in series with R3 and R4. Please kindly relate to the diagram to see where are we talking of R3, where are we talking about R4. So we are saying RP1 is now in series with R3 and R4. How do we see that? Because they are going to experience the same current, or they are going to, the same current that will flow through R3 will be the same current to flow through RP1, shall be the same current to flow through R4. So therefore, the three of them are in what? In series. So let's calculate their series resistance. So that R is going to be equal to, so I'll just call it R series. Then series is equal to 2.4. The RP1 we calculated plus 10 plus 8. We are talking about these resistors here, the 10 and the 8 ohm. Okay, so let's add that. What do we get? Of course, we are going to get 20.4 ohms. There we are. Right, that's our series there for us. Now, that R series, now that we have it, how is it connected, mind you, to the 7 ohm resistor, to the 24 ohm resistor? Remember, current, we said it was divided at this point, some current going towards this direction, some current going towards this direction, which means then the 24 ohm is in parallel, sorry, with all these other resistors. What is their equivalent resistance, all those resistors? It is this one we've just calculated, 20.4 ohms. That's the one which is in parallel with the 24 ohm resistor. So we start again another RP2. RP2, which means the other combination of resistors in parallel, is going to be equal to product over sum 20.4 multiplied by 24 over 20.4 plus 24. There we are. So if we simplify that, of course, punching that on the calculator, we're going to get 11.027 ohms to what? To 3 decimal places. Okay, so how is now our circuit looking like? I will use again, I will demonstrate again on this. So we are saying initially it was now like this. There is how our circuit was now. It was exactly like this. There was our circuit now. There was our circuit. This was the 20.4 ohm, which means it's now in parallel with the 24 ohm here. They are in parallel. Now we have calculated the effective resistance. How does our circuit now look like? So we are minimizing our circuit. That's why we are saying start from the furthest point away from the source. It makes it a little bit easier that way. Okay, so we have the 7 ohm and the 11.027 ohm that we have just calculated, 027. That's the effective resistance of the parallel combination. So how are they connected with the 7 ohm? I think the minimization of the circuit can clearly show us now. They are in series because the two are just experiencing the same current. So therefore, because of that, they are in what? They are in series. So we can therefore easily calculate the total resistance RT is going to be given by 7 plus 11.027. And that will definitely give us 18.027 ohms. That marks the total resistance we have arrived. The next question there was saying calculate the total current flowing through the circuit. I think it's now beginning to be a little bit repetitive. We can now relate very easily, which means here we can still use Ohm's law. Ohm's law, what does it say? It says current is equal to Vt over what? RT, of course, making total current the subject, right? So it means we can simply now substitute what we have. What is our V total? 48 we've been given is there at the source. Divided by R total, what did we calculate as R total? We got 18.027. So if we punch that on the calculator, what is it going to give us? It will give us 2.663 amperes. That marks our total current. So we go to the next one, I1 and I2. Apparently, the question had not indicated them clearly, so I will just label them here. I will just call this one my I1, and we'll call this one our I2, right? So let it not confuse. I'm just labeling them there so that we just have them. Apparently, they had not been indicated on the diagram. So how do we calculate I1? Let's start with I1. We can still use the current divider. What does the current divider say? It says in I1 is equals to R2 over R1 plus R2 multiplied by I total. I think you can even relate. We have, of course, the formula on the data sheet. But look, if we want current in any branch, meaning to say, suppose we want the current in this branch that we have labeled I1 towards this direction, it means we will just take the resistor in the other. That's our R2. That's why that's what R2 here refers to. The resistance in the other branch, right, divided by the sum of the resistors multiplied by the total what? Total current. So we'll simply say here R2, what it marks, what becomes our R2 in this case is 24 over, right, 24 plus, okay, R1, of course, R1 plus R2. Even if I say R2 plus R1, I also get the same answer. No worries on that. So, okay, so that we can just move along together. Let's call 20.4 plus 24, right? Multiplied by the total current. What was our total current? 2.663. And what would that give us? That will give us 1.439 amperes. That marks our total, our current I1, right? I2, we can still repeat ourselves this time around saying I2 is equals to R1 over R1 plus R2 multiplied by I total. We are no longer starting with R2, but because we understand Kirchhoff's current law, the first law, we can still say I total, current from the supply, is equal to I1 plus I2. So making I2 the subject, it means I2 is equal to I total minus I1. You still arrive, right? So what will that give us? That will give us, right? That will definitely give us I total, our total current, we have it, that's 2.663 minus I1, we have just calculated is 1.439 is equal to, what do we get? Of course, if we punch our calculators correctly, we get 1.224 amperes. I wanted again to explain, to illustrate clearly here to say, apart from using this formula here, the current divider rule. We call it the current divider rule. This formula here is called the current divider rule because, of course, we know that a parallel branch is a current divider branch. It divides the current, right? No wonder I was saying follow the conventional flow of current. So apart from using that formula, we can also still use that idea I brought in to say, what we simply do is we use the total current to calculate the voltage of the parallel branch. Why are we interested in the voltage of the parallel branch? Because we know that resistors that are in parallel have the same voltage. So if we say Vp for the parallel branch is equal to I total multiplied by Rp, the effective resistance of the parallel branch, we will get the Vp. Then we now say I1 is equals to Vp over over R1 or over the resistance of that branch. Why? Because we again know that they have the same voltage. The voltage of the parallel branch, VP, happens to be the voltage of one particular area, which means all this, and the other area again, which means we are simply saying the branches that have divided current among themselves still have the same voltages. We can still use that again, that fact again to arrive at our answer. Okay, let's quickly go to the other formula. The other formula there is saying, okay, the other question, sorry. The other question is saying, calculate the current I1 and I2. So now we are calculating I1 and I2. Okay, regarding I1 and I2, I think we have just calculated I1. We are now going to calculate I2, right? As is the norm, since I have already identified, of course, I2, so we've just done that. We've just done that there, right? We are fine. Let's quickly go to 1.4. Calculate the voltage drop across resistor R5. Okay, calculate the voltage drop across the resistor R5. We want the voltage across this resistor here, R5. As a matter of fact, it is the same voltage as the voltage of the resistor R6. They have the same voltage. Why? Because they are both in what? In parallel. So what can we do? Right. In order to find the voltage of the resistor R5, right? What we can simply do is we can just know that the voltage of the 6, since it is the same as the voltage of the 4 ohm, which is also the voltage of the effective resistance of the combination that is in parallel, the two of them, right? We can simply say, what was the current flowing towards this direction? We calculated, we got it is 1.439 amperes, right? So if it is 1.439 amperes, and what was this current here? We say it is 1.224. That's the one we have just calculated there. So we simply take the effective resistance of these two. We calculated it initially there when we were calculating the total resistance, and we got it as 2.4 ohms. So we will just say VP, which is equal to the voltage across the 6 ohm resistor, which is equal to current 1,439 multiplied by the effective resistance of this branch, 2,4. So if we multiply that, we shall get 3,4536, which apparently is 3,454 volts to 3 decimal places. Alternatively, we can also do this, but there are many ways, of course. We can just say, first things first, calculate the current through the 6 ohm resistor. How can we know the current through the 6 ohm? We shall use 1,439 as our total current. We repeat ourselves using the current divider rule. Remember, current will divide itself here. Which current is dividing itself? The 1,439 amperes. So we will use the same current divider rule. I1 is equal to R2 over R1 plus R2. I hope we are now familiar, of course, with this formula. It's becoming a little bit easier now to relate with. So we take the other resistor we don't want. We want the current through the 6 ohm, right? So instead of taking the current instead of taking the resistor, the 6 ohm resistor, we take the 4 ohm resistor. That's what this R2 is referring to. Over 6 plus what? Plus 4 multiplied by the total current 1,439. That's the current that is going to be divided between the 6 and the 4 ohm resistor. So by that, we are going to get the current through this, the 6 ohm, which is 0.5756 amperes. Then we now say, therefore, the voltage across the 6 ohm is going to be 0.5756 multiplied by what? Multiply that by 6, the 6 ohm resistor. We'll still arrive at the same answer. what do we get? We still get 3,4536, which is 3,454 volts to 3 decimal places, and we will still arrive again, right? So there are many ways of arriving at the answer, right? Let's go to the next question there. The next question is saying define a volt. So a volt is defined as the potential difference that exists across a resistance of 1 ohm when a current of 1 ampere is passed. It is passed through it, right? So that's basically the volt. Okay, let's quickly go to the next question, right? Our next question there is saying, it's again another circuit that we're having, and it's simply saying refer to the DC circuit below in fig 3, in fig 1, answer the following questions. Okay, right? It's saying calculate the total resistance. I think we can all see that that type of a question is really a very common question. We can actually see that. So what is it asking us? It's asking us to interpret a given circuit. Do you see resistors in series? Do you see resistors in parallel? And how are you going to work with them? So I always advise is always start from the furthest point away from the source. So in our case here, we have these parts, these areas here where we see I1, where we see I2 then. How are these two resistors here connected? They are in series. How about in this branch? Okay, RF4 and RF5, they're in parallel, but their effective resistance is now in series with R6, this resistor here. Right, so the term effective resistance, I hope we are now getting used to it. It's just the equivalent resistance of the parallel branch. Okay, so let's start from there. Let's start from there. So what I'm going to do, we can first simplify that parallel branch that I've indicated there. So I'm going to call it RP1. Let's start from there, right? Product over sum for those two, 17.8 multiplied by 6.8 divided by 17.8 plus 6.8. What do we get? Of course, if we punch properly, we get 4.92 ohms. Right. We have the 4.92 ohm. Right. How is this 4.92 connected to the 30 ohm? They are apparently in series, the two of them. So this 4.92 that we got is in series with the 30 ohm resistor. So let's first add them. 4.92 plus 30. What do we get? We get 34.92 ohms. Right. Now, we have the 25 and the 25 ohm. How are they also connected? They are apparently also in what? In series. How do we know that? Because they are experiencing the same current. They are, when the same current that will pass through the 25, the R2 shall be the same current that will pass through R3. So therefore, for that reason, they are in series. So let's add them as well. 25 plus 25, what do we get? 50 ohm. Now, how is the 50 ohm and the 34.92 ohm connected? These ones are now in parallel. So let's calculate RP2 is equal to product over sum, 34.92 multiplied by 50 over 34.92 plus 50, right? If we simplify, if we evaluate that, we are going to get 20.561 ohms. Okay, therefore, what then marks our total resistance? Okay, this whole branch here, this whole branch that we see here, this one, how is it connected to those other two resistors? They are in series, which means what we've just determined as our effective resistance of this whole branch is in series with the R1, with the R2, with R7, sorry, this other one. So because of that, we can still add them to say, therefore, RT, the total resistance is going to be, we are now adding 20.561, right, plus 15 plus 12, those other resistors there. And we end up having 47.561 ohms. There we are. Right, let's quickly go to the next. It's saying calculate the total current. Calculate the total current of the circuit. Now it's becoming clearer now. You can simply say now IT is equals to VT over what? Over IT. And that will give us VT. Apparently, it's given, it is there at the source. That's 120 divided by RT is the one we've just calculated there, 47.561, and that will give us 2.523 amperes if we punch it correctly on the calculator. Okay, right. Let's go to the next. So, of course, we took the total current at the supply, the 120 volts. Let's go to the next question. It's saying calculate the voltage across the 7 ohm resistor. We want the voltage across this one. Okay, what is the current passing through the 7 ohm resistor? The current passing through R7 is the total current of the circuit, which we have just calculated right now. So we'll simply say V, the voltage, is equal to I multiplied by R, remember, where I is the I total, the current we have just calculated. And what did we get it as? We got it as 2.523 multiplied by what is the resistance of the R7? That's 12 there. So what is that going to give us? 30.276 volts. That marks the voltage across the 7 ohm resistor R7. Okay, calculate the currents I1 and I2 is back again. So as usual, I would advise, of course, there are many other ways of doing it. If you can adopt any one, it's going to be good. But I will still stick to one at least, so that at least when you are making a follow-up, you can have that idea in mind by the time you are done with this question. So I will still use the same. I1 is equal to R2 over R1 plus R2 multiplied by I total, the total current of the circuit. So what is our R2? R2 is the effective resistance of this whole branch. This whole branch, the one we got is 34.92 ohms. And what is the effective resistance of this whole branch? What is our R1? It is the effective resistance of this whole branch, 25 plus 25, the one we got is 50 ohms. Right, so in using this formula, if we want I1, the current through this branch I1, it's going to be R2, so it's going to be 50 divided by the sum of the two, 50 plus 34.92 multiplied by the total current of this from the supply, the 2.523 that we just calculated there on top, right? So punching that, okay, let's substitute there correctly, okay. Okay, so it's gonna give us, okay, 50 divided by 34.92 plus 50 multiplied by 2.523, and that will give us 1.486 amperes there. Okay, let's quickly go to the other current. So I2 is going to be easier now to calculate it. IT minus I1. We will not repeat ourselves using the current divider rule again, even though we know that we can still arrive. And as I was saying, it is not the only way again of doing it. So 2.523 minus 1.486 that we have just calculated. Then if we punch that correctly on the calculator, it's going to give us 1.037 amperes. Right, there we are. Now the next question there was saying, calculate the total power consumed in the circuit. So the total power PT is going to be equal to VT multiplied by I total, as power is the product of voltage and current there. So 2.523 multiplied by 120, of course. So that will give us 302.76 watts when we punch it correctly there. Okay, so that marks the last question. So we have used these questions to try and explain how do we calculate the circuits, how do we go about simplifying circuits. That's the idea we're trying to bring out.